Okay, the lesson that we're going to do is on geometric proofs, and they're similar to algebraic proofs where you go step by step in a two-column proof and you have to justify how you got from one step to the next. This is notoriously one of the most challenging sections of geometry. The biggest reason it's so challenging is because there are a lot of definitions. If you're one of those students that are just going to refuse to make flashcards and study them, then geometric proofs are going to be very hard for you. Before you start this lesson, there's a graphic organizer that you can request from the teacher, and you can put in the description and the picture. And there's also a cut and paste activity that you're going to get from the teacher before you start. So if you don't have that yet, pause the video and make your flashcards and fill out your graphic organizer. Okay, so a geometric proof or a proof is a convincing argument that uses deductive reasoning. It logically shows why a conjecture is true. A two-column proof is what we're going to be working on. And that's going to list a statement on the left and the justification or the reason for each statement on the right. You don't need to have this in your notes at all. This is just an introduction to what we're doing. All right. So, proving segment relationships. This is your two-column proof. And at the top here, you're going to usually be given a picture. And in this case, it's a picture of a line, and then there are segments within the line. And they tell you that points P, Q, and S are collinear. We're trying to prove that PQ here is equal to the whole length of PS minus this QS here. So starting with our proof, when you're doing a reason, when you're putting a reason in, all you're doing is basically saying why you're allowed to do that. So you're going to be using a lot of definitions. So the first one, P, Q, and S are collinear. Well, that was given to us. That's right here. So that's always going to be our given. Then it says that PS is equal to, so the whole length here is equal to this little guy, PQ, plus this little guy, QS. And if you made your flashcards, you would know that that is the segment addition postulate. And we can abbreviate here. You don't have to write every single word, but as long as I know what you're talking about. The segment addition postulate, if I put numbers here, maybe it'll help you. But the segment addition postulate says that part of a segment, PQ, so 5, plus the other part of the segment, QS, 10, equals the whole length of the segment, PS, which is 15. So if I add 5 to 10, I get the whole length of the segment, 15. That's just the segment addition postulate in letters. Okay, so now I have, PS minus QS is equal to PQ. Well, what they've done here is they've mixed one of our algebraic properties. They're subtracting QS from both sides. So the QS goes away on this side, and the PS minus the QS stays as it is on this side. So all we've done is we've subtracted. Remember, that's your property of equality. Okay? And then from this statement to this statement, we virtually have the same exact thing. PS minus QS equals PQ, and PQ equals PS minus QS. So what they've done, and I'm going to write it down here, PS minus QS equals PQ, then PQ equals PS minus QS. So all they've done here, if you remember, if you fold down the middle here, this would fall on top of this would fall on top of this, and this would fall on top of this. They've just flipped our sentence around. So that's the symmetric property. Okay. And we just have to check to make sure that PQ does in fact equal PS minus QS. Okay, for the next one, we have DW, and I'm just going to mark DW here is congruent to ON. So those are congruent. And we're trying to prove that DO is equal to WN, or equal, sorry, not congruent. So DW equals ON, that's always our given. And then it says that DW, the whole length of DW here, is equal to DO plus OW. Well, once again, all we're doing is we're taking a little part of the segment, a little part of the other segment, giving us the whole segment DW. That's our segment addition postulate. Okay, and then it says ON, well, it's in the same box as the segment addition postulate. So what we're going to have to do is finish up the segment addition postulate as it applies to ON. ON, the whole length of ON, is made up of OW plus WN. Okay? Now this next one is really hard to see, so pay attention. You're going to see it very, very often, so just make sure that you're looking for these patterns. All right, down here we have DO plus OW. Well, what does that equal? Well, we said, let's look up here, we said that DW equals DO plus OW and ON equals OW plus WN. And up here, we had said that DW was the same thing as ON. So what I'm going to do is I'm going to replace this DW here with what we said it equaled down here. We said it equaled DO plus OW, right? And I'm going to replace this ON here with what we said it equaled here, which was OW plus WN. So that is the substitution property. If you did not get that, you need to rewind it and watch that again, because it is very challenging to see this one. So now I'm just replacing DO plus OW, we said it was here, equals OW plus WN. Now in the next step, OW is gone, and OW is gone again from both sides of the equation. Well, how do you get rid of something on both sides of the equation? So OW plus WN, I'm going to subtract OW on both sides of my equation, and I'll be left with DO equals WN, and that's my subtraction property of equality. Okay, so now I want you to try this one on your own. See what you can come up with. This one is going to be extremely similar to the one we just did. Okay, so take a minute, pause the video, and see what you can come up with on your own. Okay, so for the first one, that's my easy one. That's always my given. The second one, it says that MT plus TH equals QS plus SP. Now what we're doing here is we're adding the same thing on both sides of an equation, and it looks really tricky. But here we said that TH was equal to SP. And the addition property, so let's say that TH was 5 and SP was 5. The addition property says we can add the same thing to both sides of the equation. Even though the TH doesn't look to be the same as SP, it is because we said up here that they were equal. So because we said they are the same thing, then we are in fact adding the same thing to both sides of the equal sign. Now the next one, this is going to be challenging. We just have that MH is equal to, so MH, looking at our picture, is equal to MT plus TH. Well, what did we say that was? When the whole segment was equal to the two parts. That's our segment addition. So we're just going to check to make sure this one's correct. QP, the whole length of QP, is made up of QS plus SP. That's our segment addition postulate. Okay? Now, this is where it gets tricky again. How does MH become QP? Well, up here, we said that MT plus TH equaled QS plus SP. So what I'm going to do here is I'm going to take this MH, I'm going to take this MH and replace it here. So MT plus TH is equal to MH. And we said QS plus SP was equal to QP. So I'm just replacing the MT plus TH here with MH. And I'm replacing the QS plus SP here with QP. So that is the substitution property. All right. Let's look at one more example here. All right. So we're going to look at here at this example. We have all these segments. We have all these different things. AC is congruent to DF. So I'm going to just mark that on my picture. AC is congruent to DF. And AB here is congruent to DE. And we're trying to prove that BC over here is congruent to EF over here. So once again, our first thing is always our given. The second statement, it says that AC is equal to DF and AB is equal to DE. Well, if you look up here, we have these exact letters in these exact orders, but we are changing from this congruent sign to an equal sign. Anytime you change from a congruent sign to an equal sign, it's called the definition of congruent and then whatever you're talking about. And so in this case, we're talking about segments here. And the definition of congruent segments just says that segments that are congruent have equal measures. So we're just making this cleaner so that we can start using some algebra. Because we can't, this is geometry. Congruency is geometry, but we're going to be doing some algebra. That's equal signs. Okay, so number 3, we have AC. That's the whole big segment AC is equal to little guy AB plus BC. So hopefully by now you know that is called the segment addition postulate. Let's finish up DF. What do you think DF is equal to? DF is equal to DE, the little segment, plus EF, the big segment. All right, so down here, number 4, that's where it gets tricky. It says that AB plus BC equals, and I'm going to tell you it's DE plus EF, and I'm going to show you why. Okay, watch carefully. Up here, we said that AC equaled DF. And then down here, we defined what AC was. We said AC was the same thing as AB plus BC. So what I'm going to do is I'm going to replace the AC right here. I'm going to replace this AC that was given with what we said it equaled, AB plus BC. And I'm going to replace this DF here with what we said it equaled. We said it equaled DE plus EF. So down here, I'm just rewriting that, and that is allowed to be done by the substitution property. Okay, moving on, we have AB plus BC equals AB plus EF. Well, the AB stayed the same, the BC stayed the same, the DE changed to AB, and the EF stayed the same. So we need to figure out what allowed us to change DE into AB. Well, we're going to come back up here. Let me make this a little bit cleaner for you. Okay, up here is what's going to allow us to switch DE with AB, because we said that DE equaled AB. So I'm changing this DE here with what it equals, which is AB. I'm replacing it again. So that is my substitution property again. Okay, moving on to number 6. Let me clean it up. Okay. AB is no longer on this side. BC is there. AB, once again, is gone, and EF is still there. So what's going to allow us to get rid of the same thing on both sides of the equation? Well, if we subtract AB from both sides of the equation, they're gone. BC will equal EF, so that's subtraction property. And then finally, BC stays the same, but it's got a little segment bar over it. And EF stayed the same, but it's got a little segment bar over it. And the equal sign changed into a congruent sign. And like we did up here, anytime a congruent sign changes to an equal sign or vice versa, a equal sign changes to a congruent sign, we call that definition of congruent and then whatever it is we're talking about. So in this case, we're talking about congruent segments. Because segments that are congruent are also equal. Segments that have equal measures are also congruent. All right, we're going to do one more, and then you guys can go on and do your worksheet. Right here, we're told that AC, the whole length here, is congruent to BD, whole length here, and we're trying to prove that AB here is congruent to CD here. So first one, that's nice and easy. It's always your given. We said that AC is congruent to BD. And then just like the last example, everything stayed the same except for the AC lost its segment bar and BD lost its segment bar, and the congruent sign turned into an equal sign. So that's the definition of congruent segments. Okay, and sorry it looks a little funky here. There were some problems when I converted it to the smart file. But the next one, number 3, we have AC. The whole length of AC is made up of AB plus BC. And we know now that that is segment addition postulate. BD here is equal to BC plus CD. That is the segment addition postulate. All right, this is the tricky one, and you're going to start to notice that it occurs a lot. So if you can just start to notice this pattern, you'll just be able to identify them like that. Number 4. Well, up here we said that AC equaled BD. Then we defined what AC was. We said that AC was AB plus BC. So I'm going to take this AC here and replace it with AB plus BC. And we said that equaled BD. Well, down here we define what BD was. So we're going to replace BD with what we made it equal, which is BC plus CD. So we replace this BD with what it equals, BC plus CD. And that's how we end up with number 4. That's the substitution property. We've substituted their new values. All right, and then down here, AB is stayed on the line, but we lost BC. We lost BC over here, and we were left with CD. So what allows us to take the same thing away from both sides of an equation? And that is the subtraction property, because we subtract BC from both sides of the equation. And then finally, how come we lost the bar here, and were we able to take the equal sign and turn it into a congruent sign? Well, segments that are congruent have equal measures, and segments that have equal measures are also congruent. That is the definition of congruent segments. Okay, the next step here is to memorize those flashcards that you made off of the definitions and reasons that you came up with on that cut and paste activity. If you don't have those memorized, there's nothing I can do to help you. That's the initiative that you're going to have to take to be able to identify what's happening. But also, proofs are a lot of critical thinking. They are hard because you have to know your geometry. You have to be so comfortable with it that you could teach it to anybody off the street. And that's why proofs are so hard, because you're justifying what you're doing. And most students have a hard time with that. But knowing your properties and memorizing those properties is the first place to start. All right, good luck on your exit quiz.